Okay, good afternoon all. So in the last lecture, we were looking at strings. We looked at the definition of string, sentence, and related definitions like concatenation, substring, reverse of a string, subsequence, etc. Right? So let's move on to the next subtopic. That is lexicographic order or what we normally know as dictionary order, right? So this we all know this kind of ordering. For instance, we have some words, act or say ball, whatever. Now we all know that the words starting with B come after all the words starting with A are over, right? So independent of the size of the word. So in between, I can even have a very long word like maybe amendment, right? So independent of the size of the word or the length of the word, all the words starting with A will come first, and then the word starting with B, then the word starting with C, and so on. So this order is known as lexicographic or alphabetical order. Now this will work for natural languages like English or Hindi, Telugu, whatever it is, because no matter how big our language is, the number of words are finite, right? You don't have infinite words in a language. You can form infinite sentences using finite words, but the vocabulary in your language is always finite, right? No matter how big that vocabulary is. Get out. You only. Check shirt. Yeah. Get out. Quickly. So when the language is finite, it doesn't matter in which order you list the words. Alphabetical order will work. That's good enough. But suppose if we have some other alphabet like 0, 1, and there is no restriction on the length of the words in this language. All right. So if you think of all possible words or sentences that can be constructed in this language, when are you leaving? Leave quickly. Until you leave, I won't start the class. I hope you all know the new attendance rule. So just because that rule is there, I won't spare you if you are disturbing the class. It means you are losing your attendance. That's all. Okay. All right. So imagine I have only 0 and 1 in my alphabet set. I can form all kinds of words starting with 0, starting with 1, and a combination of zeros and ones. But if I try to list them in alphabetical order, how will the order look? First, I'll have 0, then 0, 0, right? And even before I want to put a 1 here, I have to write 0, 0, 0, right? Because all the words starting with 0 should be done before I have 1 at any position in my list, right? So all these words or all these sentences which are having zeros, first they should be done. All right. And after infinite such strings, I will reach 1. Then even with 1, the word starting with 1, I again should start the second letter with 0, right? 1 0, then 1 0 0, and 1 0 0, and so on. So in this sequence, there are infinite words. And in this sequence also, there are infinite words or strings. And this sequence itself this is an infinite series of infinite strings, right? Each one itself is an infinite series, and we have an infinite series of such infinite series. All right. So there is, yeah, sequence, infinite sequence, anything you can call infinite series, infinite sequence. Yes, each one is an infinite sequence, and you have many such infinite sequences. So there is an infinite sequence of infinite sequences. Okay, so that's what will happen if you try to order these in lexicographic order. All right. So how do we overcome this problem? You see, in this case, for me to reach even a finite length string, I need to take infinite steps. For me to reach 1, which is of 1 symbol length, I need to take infinite steps. I should start with 0, and then I should cover all the infinite strings that can start with 0, and only then I can reach the finite length string, that is 1. So I can't handle strings like this if they are ordered like this. I can't search for them. I can't print them. I can't do anything with the strings if I have to list them like this. So what should I do? Sorry? I can do that. So what she's saying is we can try to fix a finite length, a maximum limit to a string length, and then we allow only strings up to that length in our language. That's what you're saying. But that will be one particular language. That's something which I am building. But you can't apply that for, say, a language like natural numbers or whole numbers or rational numbers, real numbers, whatever they are. We are dealing with them. We need to deal with them. So what do you do then? That's what we are trying to do. So what kind of order? Alphabetic order is not working. Yeah. Repeating substring as a concatenation. You see, those will only be a particular subset of substrings or subset of strings. There can be strings of any pattern, right? Just take the example of numbers. All kinds of numbers you will get. Now within that, how do you reduce how many digits, sub-digits you will take? Yeah.
So how to establish an order on something like the natural numbers, right?
Mm-hmm.
So if we associate each thing in this to something in the natural numbers, in a way we have an order. So we can do that. We can associate each thing here to, we can define a rule that maps each thing here to something, a set where order exists.
Yeah, so you should define that rule. So he's saying we know how to order natural numbers. We should be, if we are able to map each natural number with one string here, then we can order these strings also according to that mapping. But even to do that, you should first order these strings in a proper way. It's not the other way around. It's not like if you map them to natural numbers, then you can order. Only if you can order them first, then you can map to natural numbers. You people are thinking too in too complicated manner. It's quite simple. We had one where. But you see this series again, it starts with 1, but even this is infinite. You start with 1, 1, even that will be infinite. You start with 1, 0, 1, even that will be infinite.
Position has a certain bar, like one place, 100 place. So you define each place by the power itself.
Then it will go to infinite place. How does defining a place stop you from going to infinity? They are ordered even now. The only question is, this order is forcing me to count infinite strings before I reach next finite string or some finite string. Can I have an ordering where I need not take infinite steps to reach any finite length string? So they gave the answer. So basically, you first order the strings based on their length, and within strings of the same length, use alphabetical order. That's it. So all strings of 0 length will come first, then strings of length 1, strings of length 2, 3, 4, and so on. That's it. Within strings of length 4, you use alphabetical order. Within strings of length 5, you use alphabetical order, and so on. That's it. Now, all finite length strings you will be able to cover in finite steps, no matter how big those steps are. Even a million length string, you can reach in finite steps. It can be million, billion steps or a trillion steps. It does not matter. But you won't take infinite steps to reach a million length string or a billion length string. It will be finite. You can reach. Okay. So that is the entire the what we want to achieve, what we want to accomplish. That is the goal. Okay. So first, let me mention. So lexicographic order is not useful to sort infinite set of strings in a language. Again, natural languages, they have a finite set of words. Your word and string are same. That's why dictionary is finite, no matter how big it is. In case you find a new word, you will find a place to insert it in the dictionary. That's it. Your dictionary won't become infinite at any point of time. It will always be finite, no matter how big it is. Natural languages have finite vocabulary, no matter how big it is. That's why you can use lexicographic order there. But in languages where whose size is infinite, which have infinite set of strings, you can't use lexicographic order. Okay? Yeah. Yes. So that's a bad way of writing or bad way of ordering. No, but you won't use words like A, 2A's, 3A's, 5A's, 10A's. You won't have such words, right, in natural languages. Whatever words you use, they will have, there are finite number of words and each word is of finite length. You don't have infinite words in a natural language. That's it. In case you want to add a word, that will be one additional word, that's all. Or 10 additional words, or 100 or a million additional words. That's it. You will never add infinite additional words. So this ordering is called short lex order. So it basically means length order plus lexicographic order. That is shorter strings precede longer strings. And we follow lexicographic order among strings of the same length. So, for instance, if we assume, say we have different kinds of strings that we can form with zeros and ones. First, we can have an empty string, epsilon, no zeros, no ones, all right? And then strings of length 1, that is 0 and 1, then strings of length 2, 0, 0, 0, 1, 1, 0, 1, 1. Then strings of length 3, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on, right? So if we look at the length of each string, its length is 0. These two strings are of length 1. These 4 strings are of length 2, and so on. And then we'll have strings of length 4, and so on. Okay, so now you can cover all the strings. Now you can map them to natural numbers. You can call this the first one, then second, third, fourth, fifth, sixth, seventh, and so on. Otherwise, you can't map without ordering them first. Okay. All right, now let's look at some more definitions. Prefix, we all know what a prefix is. If X is a prefix of Y, then there exists some Z such that xz equal to y. We know this, right? And then proper prefix if x is a proper prefix of y, or let me put it like this, x is a proper prefix of y if x is a prefix of y, and can anyone tell me what is the second condition? X is not equal to y. Or another way of saying it is z is not empty. That is, z is not an empty string. Okay, z can't be empty. So let's take an example. I can take some string, say 0, 1, 0, 0, 1, something. Now, this is a prefix, 0 is a prefix, 0, 1 is a prefix, 0, 1, 0 is a prefix, 0, 1, 0, 0 is a prefix, and the entire string is also a prefix, right? But out of all this is a prefix, but not a proper prefix. Right? Whereas these four are proper prefixes. Okay. All right. Now, we'll come to the definition of what a language is. Okay. So, a language over an alphabet. Again, even here you should notice this over an alphabet. Like a string is also constructed over an alphabet, and a language is also constructed over an alphabet. So what is the alphabet set over which a string or language is constructed? That is also important. They don't get constructed automatically or independently, right? They need some atoms out of which they are constructed. So these atoms are the symbols from the alphabet set, be it a string or a language. So both are always with respect to some alphabet set. You should always keep in mind. Okay. A language over an alphabet is a set of strings over that alphabet. That's it. The definition is quite simple. You have an alphabet, you can construct some strings over that. If you take some set of strings which can be constructed over a given alphabet and group them, that will be a language. So you can form potentially infinite languages over one particular alphabet string, one particular alphabet set. Okay, so let's look at some examples. So let sigma be equal to 0, 1. This is a language or alphabet set? This is alphabet set. Okay, so keep that in mind. This can also be a language, but usually we use sigma for alphabet set. We don't use sigma for language. Okay. So one language which you can build out of this can be maybe all strings of length 2. Okay. So those will be 0, 0, 0, 1, 1, 0, 1, 1. Can there be any other elements in this set? Any other strings in this set? No, these are all only 4 possible strings are there of length 2 over the alphabet set 0 and 1. Okay, so this is one language. So we can describe this language as a language which has strings of length 2 over what? Over sigma, over the alphabet set sigma, not any strings of length 2. They should be built out of 0 and 1 only. You can have some other sigma which is having A and B, or it may have 3 letters or 5 letters or something. over that sigma you will get a different language of strings length 2. Okay, so if you are considering the alphabet set 0 1, over that you will have only this language with strings of length 2. Okay, so let's look at another language. Suppose I want to build a language where some k zeros are followed by k ones, where my k is greater than or equal to 0, which means suppose I have 2 zeros, they should be followed by 2 ones. I have 5 zeros, they should be followed by 5 ones. I have 1 0 followed by 1 1. I have no zeros and no ones, which means empty string is also allowed. Okay, so the strings in this language, empty string is an element, right? Because that satisfies this condition. No zeros followed by no ones. So it satisfies the condition. So epsilon is a member, and then 0 1 is a member, and then 0 0 1 1, then 3 zeros, 3 ones, 4 zeros, 4 ones, and so on. Okay, so here this is a set of strings with k zeros followed by k ones, where k is greater than or equal to 0. Okay, so it can start with 0 length string. I can choose to start with k greater than or equal to 1, or I can choose to start with k greater than or equal to 10. It's my choice. I need not always include all the strings which satisfy this condition. I can have a very complicated membership condition for my set membership. All right, this is one condition. I can change the condition slightly, this parameter, that parameter, anything. So let's look at another example. Suppose now I don't worry about the order, but I only worry about the frequency of symbols. All I need is all those strings with equal number of zeros and ones. Now it does not necessarily mean that zeros should come before ones. Even 1 0 is allowed, or 1 1 0 0 is allowed, or 1 0 1 0 is allowed, or 0 1 0 1 is allowed. Anything is allowed as long as the number of zeros and number of ones are same. Okay, that can be a language, right? So, and now I will say it should be of length minimum 1. I don't want empty strings. Even empty string can be allowed, but I just choose not to. It's up to me. Okay, so 0 1 1 0, then 0 0 1 1, 0 1 0 1, 0 1 1 0, 1 0 0 1, 1 0 1 0, 1 1 0 0, and so on. All these are strings with equal number of zeros and ones. Here order does not matter, right? So this is another language.
We know that if you compare the numeric values, it's different. But we're using another language to say that these two numbers are different. These two strings are different in this language. If we stay in the same language like LC, how do we know? Like 0011 and 010 are different strings.
They are different. The order is different, right? You don't need to convert them to corresponding decimal values. First of all, I didn't say these are binary values. They're just some symbols. Instead of 0 1, you use AB. Okay, it's like AB, BA, AABB, ABAB, like that. So AABB is different from ABAB.
What matters
Order matters. I mean, order does not. Here in this case, I am following the order. As long as you can list them, it does not matter. In this case, it is a set. So technically, order does not matter. But in case you want to order them, then you should follow some method that is shortlex order. So I didn't exactly get your question. Are you asking about order or are you asking about conversion to decimal? What?
How do you differentiate 0011 from 0101?
They are different. What?
That order of the digits, order of the characters doesn't mean as anything in the string. Then how do you differentiate these two? Just like for a language, the order of characters should matter for the string. I'm asking that question.
Simple. When do you say two strings are equal?
If they are same length.
Everything is same. The sequence of letters and the length of the strings, everything should be same. If any one of these differs, two strings are different. That's it.
That's what I'm asking. Like when we talk about strings, is it by default that the order matters, or is it to define that for this language?
You need to understand two things: order of strings in a language and order of letters within a string. Okay? Order of letters, the moment it changes, it's a different string. In whatever order you write them, in whatever order you list the strings, I can write 0011 after 0101 or before 0101. They are still different strings. So the order in which the strings appear is immaterial to their identity. Strings are either different or same, whichever order you write them in. That's all.
But by defining string, if we follow the definition of string, that doesn't make clear that which string is equal to, like, that doesn't make clear as that is 0011 and 0101 different from each other, because they have the same characters in them, they have the same length, so they should be same string. They shouldn't be different string.
Who said they should be same?
By the definition of the string.
Yeah, who said definition of the string is, it only says they are strings. It does not say they are same strings.
But it doesn't say they are different strings.
Okay, we will come up with a definition to say they are different strings. It's like, it boils down to the definition of the different elements in a set. If A and B are two elements in the set, what prevents me from saying they are same? I will say all the elements in the set are same. Now, why to stop at length? Even if their lengths are different, I will say they are same. When you're saying even when the characters are different, they are same strings, I will say even when the lengths are different, they are same strings. What is stopping me? That's it. It is evident. It's like two things constitute any string. One is the symbols, second thing the order of the symbols. If any one of these change, the string is different. That's it. So here, these are strings with k zeros and k ones in any order, where k is greater than or equal to 1. All right. We can construct any arbitrary language also. It's not necessary that every language should have a pattern. All the strings in the language should satisfy one condition. They can be arbitrary. It's like set, right? Sometimes the elements of a set may have something in common or they may not have something in common. They can be just arbitrary. One is like a set of people. All elements have a commonality that they're all people, or a set of chairs, tables, etc. Or I can just have a set of arbitrary elements, some chair, table, projector, person, horse, dog, whatever it is. It's just a set. That's it. That's also a valid set. it's an arbitrary set. Similarly, a language, it's not necessary that the language should have some pattern in its strings. Language is nothing but a set of strings over an alphabet. So you can have an arbitrary language also, like for instance, something 0, 1, 1, 0, 0, or 1, 1, 0, 1, 0, 1, 1, something. Okay, anything. It can be any language. Just an arbitrary set is also a language. Okay. All right. Now let's quickly move on. So the next subtopic is Boolean logic or binary logic. You see, these topics now which I am discussing, they are all in the textbook. They are from chapter 0, like from set theory when I started from lecture 6. They are all from chapter 0 of the textbook. Whatever I discussed before that in the first 5 lectures, the history of computation, Turing machine, whatever story I said, that is not part of the textbook, and that you will not find any single resource where you can get all those things. You can search for individual terms, and over internet you will find videos, Wikipedia articles, etc. So mostly the lectures will be sufficient. I will also upload the lecture recordings and I'll share with you, but lecture notes, this is sufficient. In case you want to search, you should search independently. But from lecture 6, from set theory, whatever I'm covering, it is there in the textbook. Okay, so it is chapter 0, and so from lecture 1 up to the end of chapter 0, which we'll cover before minor, that is part of your minor exam. We may touch or start chapter 1, etc., but that will not be part of the minor exam. Chapter 0 ending will be the part of minor exam. Okay, and we will have a makeup class on Saturday online, because it's difficult to find a common time when all of you are free during weekdays. So we'll have a makeup class on Saturday. I'll send you a mail, maybe around 12 o'clock. Okay, fine. Yeah, so this is all there in the textbook. You can refer to the textbook also. All right. So you all know what Boolean logic is. So let's quickly go through that. Boolean logic is a mathematical system built around two values, true and false. These are what we call as Boolean values. And this also we know usually true is represented as 1, and false is represented as 0. Okay. We can manipulate Boolean values with Boolean operations. So you already know of some Boolean operations, right? Like and, or, not, implication, and by implication. Okay, so technically even these 5 operations also can be reduced to 2 operations. We will see that. But traditionally there are 5 Boolean operations. Okay, so is and, or, not, implication, and by implication. All right, and you also know of truth tables. We'll just quickly touch upon that. So for example, if we take an AND operation, so we know 0 and 0 is, what is 0 and 0? 0. 0 and 1, 0. 1 and 0, 0. 1 and 1, 1. It's like true and true, true and false, like that, right? Now, like in programming, we can do arithmetic with numbers in 2 ways. Either we use the numbers directly, or we store these numbers in variables and perform calculations on them, right? So I can do 2 plus 3 calculation by actually entering 2 plus 3, or I can store 2 and 3 in 2 variables x and y, and I can do x plus y. Okay. Similarly, in logic, we can use statements which have these values, truth values, which take upon these truth values. Okay, so again, same thing. 0 0 is 0, 0 1, 0 and 1 is 0, 1 and 0 is 0, and 1 and 1 is 1. All right, so either you directly deal with the truth values, or you perform Boolean operations on statements which can take these truth values. Okay, Boolean operations are fundamentally actually performed on truth values, but that is not of much use to us, because doing 0 and 1, 1 and 0, or 0 1, whatever it is, I know what true and true means. It will be true or false, etc. But I want to apply this in some real life scenario. So that is where we arrive at logic which can be related to reality, right? Like when I discussed formal systems, when they try to model reality, you are dealing with some statements like all men are mortal, Socrates is a man, therefore Socrates is mortal. So here, what are you doing? You are doing some kind of logic, that's fine, but by assigning truth values to the premises, you are sort of deriving the truth value of the conclusion. That is through some logical means. Okay, and you are doing Boolean logic of sentences, but technically you are doing Boolean logic with their truth values. It may seem as if you are doing logic on the sentences, but technically you are doing logic with the truth values which are assigned to the sentences, right? So it's like programming. when you do x plus y, x and y themselves as symbols don't have any meaning. When they are replaced by their corresponding values, only on those values you can perform the addition operation. Similarly, even when you use symbols which represent prepositions or statements, it is on their truth values, not directly on the statements, that you can do Boolean logic. But on the truth values of the statements, you can do Boolean logic. Okay? So, instead of 0 and 1, we can also use symbols which represent statements or prepositions like P, Q, etc. and assign values, that is 0 or 1, to these symbols. So if we look at an example, it looks something like this, right? So we just saw it. We know P and Q. I can write something like P and Q. But this AND operation is not defined on symbols P and Q. It is defined on truth values, true and false, or 0 and 1. It is defined only with those inputs, for those inputs. Okay? But we normally use this P and Q, P or Q, etc. It means that the truth value of P and the truth value of Q are taken, and on them this AND operation is performed. Okay. So in this representation, this is called operation or operator, and these two are called operands. Okay, fine. Now I mentioned all Boolean operations can be reduced to two operations, right? So let's just see that. All Boolean operations can be reduced yeah, tell me. Tell me. How come it's not 4:30 yet, right? Still some 3 minutes are there. Oh, okay. It is and not. It can be represented as this or this. Okay. So let's define, say, OR operation first. So OR operation is nothing but not of not P and not Q. So once we define an operation, now we can use that to define other operations. So P implies Q is not P or Q, and P by implies Q is P implies Q and Q implies P, right? Yeah, and you can also include, say, XOR, right? Like P implies Q, P XOR Q is not P and Q, are not Q and P, which means if Q is true, P should not be true, and if P is true, Q should not be true. They should have opposite values, which is equivalent to saying not of P by implies Q, right? All right, so let me stop here. And,